Here we continue on with our analysis of an inverting amplifier with just a couple of examples that have numbers in them. Remember we came up with that the closed loop gain V out over Vin is minus the ratio RF over R1. So if we selected resistor values such that the feedback resistor was 330k ohms and R1 was 30k ohms, we would have a closed loop gain of minus 11. So let's see what that means here. If we had a DC voltage at our input, say a DC voltage of 1 volt, well, with this closed loop gain we should expect an output that's 11 times greater than V in, and also the minus means that it's 180 degrees out of phase. So if we have 1 volt at our input, we would expect V out to be minus, a DC voltage of minus 11 volts. Okay, now this is provided that the minus V power supply source is minus 11 volts or more negative. Okay, so we would get the expected output of minus 11 volts provided that this negative power source was at least the negative value of minus 11 volts. If it's more negative than that, like minus 12 volts, minus 13 volts, and so on, well, we would also still get this expected value. However, if the negative power source was something less negative than minus 11 volts, like let's say minus V was minus 10 volts, well then instead of getting this expected output of minus 11 volts, what would happen is that V out would just hit that lower rail of minus 10 volts, and that's what our output would be. So even though we were expecting minus 11 volts at the output due to the resistor values that we have, if our negative power source is some negative voltage that's less negative than this expected output, well, the output would just equal that less negative value. And when this happens, we say the output is distorted because it equals a value that's other than what the expected value was. Alright, so that's a DC example. An AC example is that if we had a sinusoid, a 1 volt sinusoid, as you see here, 1 volt peak sinusoid, well, with the same resistor values and the same closed loop gain, we would expect an output sinusoid that's 11 times bigger than this input sinusoid and also 180 degrees out of phase. So we would get, or expect to get, a sinusoid that looks something like this. Oops. Kind of a squirrely kind of sinusoid, but the point being that we would expect a sinusoid that would vary between minus 11 volts and plus 11 volts, and it's 180 degrees out of phase. During the positive half cycles of the input, we have a negative half cycle at the output, and during negative half cycles of the input, we have positive half cycles at the output. Now again, this would all be true as long as the rails, in this case both power source values, have magnitudes 11 volts or greater. If, say, I'll use a different color here. Okay, if our rails were something less than a magnitude of 11 volts, like say for example, if the plus power source was 10 volts and the minus power source was minus 10 volts, well then we would get clipping, that the output couldn't exceed those rail values. So here the positive peaks would be lopped off at plus 10 volts and the negative peaks would be lopped off at minus 10 volts. Okay, because V out can never exceed what the rail values are, like we discussed in the first video about op amps. Alright, well, one last thing in our analysis of an inverting amplifier, and that's to get what the output current is. So here I just drew the output part of the circuit, just what's relevant to this analysis. So this here is the output of the op amp, and this current at the output of the op amp I have labeled I0, and that's what we want to find, is what that output current is. So we got our feedback resistor of 330 k ohms, and then VA, remember, was 0 volts, so I just have that represented as ground since there's 0 volts at ground. And then I added a load resistor here at the output. And by the way, for an ideal op amp, it doesn't matter what's connected at the load as far as when you do your analysis of V out over V in. So whether we had nothing connected to V out, like when we did the analysis for the closed loop gain, or whether there's some resistor connected between V out and ground, the analysis would be the same as what you saw previously in the ideal case. So and then we're going to use the value of V out being equal to minus 11 volts in this analysis. Okay? Alright, well, to get this current, all we're going to do is we're just going to do a Kcl equation here at this node, okay, the V out node. So this current through the load resistor, since there's ground on the bottom side and minus 11 volts on the top side, well, it's going to be flowing like this. And likewise, the current through RF is going to be flowing from ground to V out where minus 11 volts is. So IRL is just going to be 0 minus 11 divided by 10K. Okay, and that comes out to 1.1 milliamp. And then IRF is just going to be 0 minus 11 over 330K, and that comes out to 0.033 milliamps. Okay, so you see both these currents are flowing into this node, so that means the current here, I0, really is going the other way. See, I0 is really going that way. So if we leave I0 defined as this direction, we would show the value as minus, okay, minus the sum of these two. So 1.1 plus 0.033, and that's going to equal an answer of minus 1.133 milliamps. Okay, of course, if you redefine the direction of I0 going, the actual direction from right to left, well, then we would just show this value as a positive number, as you learned in circuit theory, that the minus sign in front of a current just means that the indicated direction is actually the opposite way. So when you're doing, or when you're finding the output current of any op amp circuit, I mean, this is an inverting amplifier example, but the same is true no matter what kind of op amp circuit you have, and we're going to get to many others coming up in future videos. So regardless what the op amp circuit is, it's always the same approach to find this output current. You're just doing a KCL at this node V0.